Hello class, here's the video summary for Chapter 6, Section 6.1 and 6.2. In this chapter, we'll be learning how to perform hypothesis tests without any bootstrapping under certain conditions, namely the central limit theorem or some other information. We'll be learning several different hypothesis tests, primarily concerned with means and proportions. Note that we will still use bootstrapping for hypothesis tests for correlation. We'll also learn to compute a couple different confidence intervals. Section 6.1, distributions for a sample proportion. And notice that if we have the sample size and the proportion, then we can compute the standard error directly. We don't need to have a sigma or anything like that for proportion. And using the central limit theorem, we can approximate the sample proportion distribution by using the normal distribution. It's important to note that the larger the sample size, the better the approximation is, and that there are certain technical restrictions and for when we're allowed to use the central limit and not, namely n times p greater than 10 and n times 1 minus p greater than or equal to 10. For example, 6.2 in the text, if we know that 80% of all flights of a particular airline arrive on time, and we randomly sample 400 of them, what does the distribution of possible outcomes look like? So if I were to actually sample 400 planes, I'd probably get something close to 80%. And if somebody else did, they'd probably also get something close to 80%. But what does that variation of distributions look like? Well, using the central limit theorem, we know that the distribution is normal, approximately normal, with a mean of 0.8 and a standard deviation of 0.02. If we hop over the advanced normal distribution calculator, we can enter in that. Let's just make this confidence level 0. And we see that indeed, if across all flights 80% of them arrive on time, then most of the samples that we take will also be about 80%, but this is a variation, and notice that it shouldn't be so uncommon to see as low as 76%, all the way up to say 83–84% should be considered a typical sort of observation. Section 6.2, confidence intervals for single proportion. And notice that in order to use the central limit theorem and not bootstrapping, we have a similar restriction as before, where p hat is our sample proportion given here. And if these restrictions hold, then we can use the central limit theorem, and it's given by this. Of course, the advanced normal distribution calculator will do this calculation for us, but it is centered around our sample proportion, give or take a certain amount. Example 6.3. Okay. This is a question of mixed nuts, as in what proportion of nuts in a bag of mixed nuts are peanuts. And so if we took a random sample of 100 nuts, we would see that we got that 52 out of 100 were peanuts. And so we want to know, well, compute a confidence interval for what is the true proportion of nuts that we'll find that will end up being peanuts. So let's work that out. Again, our sample proportion is 0.52. Our sample size, we sampled 100 nuts, and we want a 95% confidence interval. And this is our confidence interval visually. But we see that it's about 42.2% to 61.8%. That is, we are 95% sure the true proportion of peanuts in the mixed nut bag from this company are between 42.2 and 61.8%. Notice from our middle of 0.52, this gives us a margin of error of almost 10%. Section 6.2 also shows us how to determine sample size, a minimum sample size, in order to get a requested margin of error. So again, we have about a 10% margin of error here. If we wanted something much smaller, then we need to sample more, and this formula will tell us what to do. Again, the advanced normal distribution calculator will do the number crunching for us. But we do need to know what our requested margin of error is and some proposed proportion or estimate of the true proportion, and then z star is based on the level of confidence. Example 6.5. So to do this, as an example 6.5, we can go to the sample size for confidence intervals for proportion in the advanced normal distribution calculator, and we enter in our values, which are already entered here. And this tells us we need almost over 13,000 samples in order to get a 1% margin of error in this particular situation. And note that this number is a little bit different from the number provided in the book. There's some rounding issues here in the way things are calculated. But again, in order to produce a margin of error of 1%, it's a really small margin of error, we will need about 13,376 different samples. Alright, that's it for chapter 6.1 and 6.2. I'll post 6.3 and so on a little bit later. Take care.